Hello, welcome and thank you for joining this webinar on air mobility. This is the first session on autonomous aerial system development trends. My name is Fred Noto from Industry Marketing, and I'm in charge of the Robotics and Autonomous Systems area. It's a pleasure to be here. And in this first session, I aim to give you a very high-level overview of the solutions and capabilities that MATLAB and Simulink offers for developing autonomous aerial systems while introducing customer stories as well. So let's get started. But before we get into autonomous aerial systems, I do want to mention that MathWorks supports the development of a variety of different autonomous systems, ranging from robotics, which includes industrial robots, robot arms, mobile robots, automated driving systems, marine robots, and the topic for today, unmanned aerial vehicles. So let's get into the aerial system side. And I'm sure you have all seen this in recent years, but usage of aerial systems is increasing, accelerating, if you will, across a variety of applications and industries. Of course, aerial systems and drones have been used in educations to teach our youth, as well as filming and entertainment. It's used also for agriculture and construction applications, for surveying and measurements. And it's being used more and more for inspections, surveillance, and monitoring, as well as delivery, transport of cargo, logistics, if you will. And we also see development in air mobility or flying taxis as well. Now, there's a need for scalability of aerial system operations as the usage is increased. So rather than one pilot for one aerial system, we're seeing an explosion of autonomous flight technology development so that an operator could manage, monitor multiple aerial systems all at once. So that is one of the mega trends for aerial system development, right? Autonomous technologies applied to aerial systems. And there's also innovative mobility systems being developed as well, beyond just multi-rotor or fixed wing and into VTOL configurations as well. And as these aerial systems are becoming used in society, there's a larger focus on safety, reliability, robustness, so that it doesn't crash and hurt anybody on the ground. These systems are incorporating AI technologies for intelligence to be able to more efficiently execute these tasks, and incorporating aspects of big data for efficiency in operation and IoT for connectivity as well. Digital transformation is being embraced for research, development, and operations because flying hardware and testing on hardware is really risky. To summarize, aerial systems are beginning to integrate autonomy and intelligence for assuring safety and reliability while maintaining efficiency in operations. So now I want to switch over to another perspective, which is the integrated development workflow for developing autonomous aerial systems. And you could do a lot of things within the MATLAB and Simulink ecosystems, which I want to start off with. You could define your requirements and design system architecture. You could then do more detailed modeling of your aerial system, including the plant model and control system. You definitely, most likely, want to add autonomy, and this would be designing autonomous algorithms, which include perception, motion planning, decision, and control. Verification and validation is necessary to ensure that these systems will operate in a safe manner. And perhaps there's some certification aspects as well. You can link with external simulators as well to perform closed-loop simulations with sensor models. After ensuring that your autonomous systems work, you could automatically generate code from your models and algorithms to deploy to hardware. Connect to the hardware for flight testing, and after flight test, bring in the data, analyze it, and get your insights from it. Right? Now, I do want to introduce first a customer story of this overall workflow, which is from Yamaha Motor Company in Japan, who developed a series hybrid system for drones and executed flight testing using model-based design. And this is a very realistic approach because they had the goal of developing a series hybrid system for a large-scale drone, but they started small. They started with a small electric drone to be able to understand that the vehicle dynamics control systems would work as expected, and then scaled upwards to a larger design. And they also incorporated code generation for efficiency in the development process. So this is a really good example of utilizing model-based design for developing aerial systems. Now, there's different type of engineers involved with development of aerial systems. There's the aerial system developers who build new systems to go and fly. And then there's aerial system services who use these aerial systems to gather data and get insight from. But there's also folks in between as well. There's engineers who develop new autonomous technologies to implement onto your aerial systems. Right? Now, I want to step through each of these engineer types to see what they would be doing in their development tasks, starting with those that build aerial systems. So back to this workflow. Let's first zoom in on the system architecture, right? You first want to have an idea of the system that you want to develop, which typically starts with research and development or defining requirements. And you could define your requirements within the Simulink ecosystem as well through requirements toolbox. But you could also utilize a system composer for your model-based system engineering development side as well, your process as well over here. System Composer allows you to interactively define your architecture components within this canvas, connect them, and define your interfaces between them as well. Right? So at the end of the day, you have a top-level view of the system architecture of your aerial system, in which you could drill down even further and define your detailed models within each of these components as well. You could even go back and link your requirements to specific components of this model for traceability as well, to ensure that you're designing what's been defined in the requirements. Okay. So moving on, after the architecture is defined, you would want to model and simulate your aerial systems in more detail. Right? So this really starts off with plant modeling and control design. And as far as plant modeling goes, there's different methods to model your plant, your aerial system plant model, right? So the key point here is to select the plant modeling methodology that most is applicable to your task at hand. If building new aerial systems, you most likely need a detailed model of the system, which is the high fidelity model. Now, we offer capabilities to use physical modeling processes, methodologies to design your plant models. So this would be connecting mechanical components of your aerial system or adding electrical components such as motors and batteries as well for a more CAD-like approach to modeling your plant model. If you have equations of motions, you could model those in Simulink as well. We also offer some blocks to quickly model your vehicle dynamics for equations of motion, such as 6DOF and 3DOF blocks here. And if you just want to quickly represent some sort of aerial system in a simulation, we offer guidance model blocks here so that you could quickly get up and started with modeling and simulating multi-rotor or fixed-wing aircraft. All right. This will be covered in more detail in a later session. And with these plant models, you could then design your flight controls as well, integrated together to simulate in MATLAB and Simulink with model-based design. You could also add a visualization, as you've seen here, in the form of the environment simulation visualization, as well as gauges to see your altitude and airspeed and other characteristics of your aerial system while in simulation. Okay. And customer reference for novel aerial system design is from Tecnalia over in Spain. Tecnalia was developing electric propulsion system for new aerial type systems, and they did so using model-based design in two ways, both with physical modeling and with using Simulink to model equations of motion, the vehicle dynamics, right? And you can see the system that they model here. It's a very new type of aerial system, which is neither a multi-rotor or a fixed wing, but more a VTOL configuration. And by comparing the two methods of modeling, they were able to understand result in the fact that the results are very similar at the end between these two methods. Right? So Tecnalia used model-based design to develop a novel type of aerial system here. Now let's move on to the aerial system services side of things. Those that don't build new aerial systems, but rather use go out and fly aerial system to gather data. and they want to flexibly build solutions and accelerate data analysis after flying the system. Now, this is not a new concept. Aircraft, drones have been used to gather aerial imagery, aerial data for many years now. Here's an example of one such case, right? So an aerial system will fly at a specific altitude to gather imagery data of a specific vegetated area or a farmland area. And typically, you can, well, sometimes you can easily understand which areas are problematic and perhaps not doing too well. But recently, computer vision image processing techniques are applied to the payload data, to these sensor data, to automatically identify areas which are perhaps stressed or unhealthy, right? So you could clearly see that highlighted on the right side. Another example of this is processing of aerial LiDAR data for segmentation. So again, an aircraft is flown to gather aerial LiDAR point cloud data, and this is processed using deep learning techniques as well to segment between the ground, vegetation, houses, cars, and other objects within this scene. Right? So deep learning is used on this LiDAR point cloud data to recognize between different objects within the data. So that previous example incorporated deep learning, and I believe that AI is typically included in these sort of computer vision algorithms as well. And MATLAB really provides an end-to-end workflow for designing, evaluating, deploying your AI algorithms, starting with data preparation, importing, pre-processing your data, AI modeling, which is developing new AI models or importing existing models, simulating and testing to ensure that your AI algorithms are performing as expected, and then deploying to embedded devices, enterprise systems, or the cloud down the line as well to share this application. Again, we saw an example previously, but in that previous example, we read in LiDAR point cloud data, did some pre-processing, applied PointNet plus segmentation techniques to be able to recognize different objects. And then beyond that, you could utilize virtual testing or 3D simulations to verify that these algorithms are performing as expected. And once verification is complete, you could generate the code and implement it to hardware or deploy to some enterprise systems, right? Now, again, this is not a new concept. It's being used in a lot of different areas, different application areas, right? Highlighting here again is the agriculture case. This has been done for years now, where drones are piloted and flown in a specific farmland area to understand healthy fields versus perhaps some fields that are not doing so well. And in recent years, there's been advancements in computer vision and AI algorithms to not only be able to identify perhaps this is not doing too well, but perhaps the reason why it's not doing too well, whether that is lack of nutrients or whether that is pesticides, so that you have more insight into how to react to the current situation. Right? So again, on the aerial system services side, these are folks that are building algorithms to implement onto the payload data, if you will, here. Now let's get into our last category of engineers, who is the algorithm designers. Now these are folks who are developing new autonomous technologies to be implemented onto the aerial systems. And they want to test these new algorithms that they develop without hardware, because if you could imagine, you build a new algorithm, if you want to go fly it, you want to make sure that it's going to control the system very well, or else you might damage your actual hardware, right? So getting back to our workflow over here, this starts off with the design algorithms phase. So this incorporates designing your perception, planning and decision, as well as controls algorithm, right? And MATLAB and Simulink provide, let me step back for a second, talk about what this encompasses. So you have an aerial system which starts off at a specific location, and it needs to navigate through some obstacles within a given environment. It wants to get to an endpoint to perform a specific task. So it needs to plan a path between these obstacles in the environment. and control itself along the path so that it's not colliding into anything along the way, right? So that's what's encompassed within perception, planning, decision, and controls. And MATLAB and Simulink, along with add-on products, provides a lot of different capabilities to help you in designing these autonomous algorithms. For perception, this really encompasses two major sections. The first one being self-awareness or localization, understanding where the aerial system is within a specific location, right? So this typically incorporates sensor fusion techniques to utilize different sensor modalities to further have a precise localization information. So perhaps you may want to use IMU or GPS data, fuse that together to understand your position and orientation within a certain coordinate system. Another method is to understand your relative position within a localized map, right? So that could incorporate simultaneous localization mapping techniques, or SLAM techniques, if you will, right? The second part of this is situational awareness, or understanding the objects around the aerial system, right? So as the aerial system flies around, it doesn't, you don't want it to bump into anything. You don't want it to collide. So you want to be able to identify objects in its vicinity, right? So this typically incorporates sensors for perception, such as cameras or LiDAR, right? And again, this leads into some computer vision techniques, which typically includes deep learning AI as well, right? So identifying humans to track them, or identifying birds to avoid them, identifying trees to plan a path around them, or buildings so that the aerial system could fly in between them, right? So different forms of identification, recognition algorithms will come into play here for perception. Okay, so that is on the perception side. Next is planning and decision, or how the aerial system will autonomously fly. On the left side, we have some classical methods of path planning, which is waypoint and orbit following. So for waypoint following, it's basically defining some points within a given location for the aerial system to fly through. It's a very basic way to do some path planning, but add-on product of UAV Toolbox provide capabilities to define these sort of missions, if you will, right? There's more advanced techniques for path planning as well that incorporates path planners such as RRT or A-star and others as well. And Navigation Toolbox is another add-on product that provides these path planner algorithms so that you could set a start location and end location, perhaps an intermediate point as well. And the path planner would calculate a efficient path between those points within a given environment. Okay, so that is on the path planning decision side of things. And lastly is onto controls. So once the path is planned, the aerial system needs to navigate along that path with as little error as possible, right? And there's some traditional methods such as PID controls for this, but there is a lot of research into applying more advanced techniques such as model predictive control as well as reinforcement learning techniques for this. So examples of this is applying nonlinear MPC for trajectory tracking, or utilizing reinforcement learning techniques to generate trajectories for the aerial system to fly along. So controls for this can go beyond PID and include some newer, more advanced techniques such as MPC, model predictive control, and reinforcement learning. An example, a little bit more on the perception side for autonomy is from India, a researcher in India of development of real-time object tracking algorithms for UAVs. So as the UAV flies in a specific location, the sensor, the image data is processed to identify specific objects within its flight. And potentially this could lead to modifying the flight patterns depending on what's identified. So again, this is using computer vision techniques to be able to identify objects from aerial imagery data while in flight. Okay, so we just talked about designing algorithms and how various add-on products could help you in designing these advanced autonomous technologies. But once these algorithms are designed, you want to verify them through simulation. And for autonomous algorithms, this typically is a simulation with sensor models, right? Especially if perception is involved. And MATLAB and Simulink allows different methodologies to do this, both within MATLAB and with co-simulation. So within MATLAB and the add-on product of UAV Toolbox, we provide capabilities for cuboid simulation. And we could also co-simulate with the Unreal Engine 3D simulation environment as well. This will be again covered in a later session, but cuboid simulation could be a good first step for closed loop simulation with sensor models. You could define an approximate environment of that the UAV or the aerial system will fly, and add some localization sensors such as GPS IMU, as well as LiDAR in this case as well, to do some initial verification of your autonomous algorithm. On the right side is more photorealistic 3D environment, which is co-simulation with the Unreal Engine. So you could co-simulate with this gaming engine to be able to generate synthetic camera or LiDAR data, which is then fed back into your model for that closed loop simulation, right? So your algorithms in the model could react to the 3D scenes as well here. There's also capabilities to import terrain data so that the environment is more representative of the actual environment the aerial system will fly. And you could also add weather effects such as rain, fog, or the position of the sun, so that you can test your autonomous algorithms in a variety of different environmental test conditions. That may be hard to replicate in real world as well, right? So again, this is closed loop simulation with sensor models to evaluate your autonomous algorithms. And not only can these closed loop simulations with sensor models help in verification of autonomous algorithms, but it could also help to generate synthetic data to help design your autonomous algorithms as well. We all know that going out and flying your actual aerial system and gathering real data would be the best, but that is oftentimes very time-consuming, very costly to do. So in many cases, 3D simulation can be used to augment real aerial data with synthetic generated sensor data, so that you could add some additional data points to design and test your autonomous algorithms. There's also tools to help you design scenes for these simulation environments as well. Again, this will be covered in more detail in a later session, but add-on products such as Roadrunner could help you design scenes that are perhaps custom scenes for your simulations, aside from the default provided urban city scenes or the suburban scene, right? So we have tools to help design these 3D scenes as well. All right, a user story for system level simulation is from BAE Systems, who has been developing unmanned air systems for quite some time now, but they are using model-based design to do so in many cases. So again, modeling and simulation of their integrated system beyond just plant and controls, flight controls. They also use it for specific component design, such as actuation modeling and environment control systems, and also goes as far as image analysis as well, right? So that image processing side of things comes into play. They also use our tools for flight data plotting, analysis of data after the fact, if you will. Okay. All right, very briefly, we did cover designing autonomous algorithms as well as simulating them in closed loop simulations. The next step would be to deploy to hardware. Again, you want to move from virtual to real environments, and we provide solutions for automatically generating code specific to the hardware that will be used. You could generate C code for deploying your flight control algorithms to autopilot hardware, such as the Pixhawk. We could also generate CUDA code for deployment onto NVIDIA Jetson GPUs, which most likely will be used for some of the heavier autonomous algorithm processing. Right? So again, automatic code generation is also available. You could also connect to some specific MAVLink supported hardware in flight so that you can monitor these aerial systems while they're flying around and you're doing some flight tests. And you could do post-flight data analysis. We talked about payload data analysis on the services side, but we offer some strong capabilities for flight log analysis to ensure that your aerial system is flying in a stable, reliable manner. And I do want to highlight this very quickly. This is a tool called the Flight Log Analyzer. So we can get it started here. But this Flight Log Analyzer app is an interactive tool to help you import flight log data, U-log, T-log, as well as custom data as well. Visualize it within a mapped environment. So you could visualize the trajectory. You could generate some typical plots that you would use in data analysis, right? It also allows for interactive zooming in on specific locations in the data and allows you to share this data session with your colleagues as well. So this is a very powerful tool for data analysis, visualization, and analysis. All right. Moving on to verification validation, which will be covered again later in the session in more detail. But there are a lot of different verification validation capabilities through add-on products. These could incorporate requirements traceability, so you could understand that you're modeling the correct things. Test management and automation, which will help you be more efficient in executing your various test cases, and evaluating completeness to ensure that there's no errors or bugs in your model, in your design as well, right? This also connects to safety and reliability with certification as well. A lot of these verification validation capabilities are qualifiable and can be used within certification workflows as well, such as for DO 178 and DO 254. So again, we offer capabilities for not only modeling and simulating new systems and autonomous algorithms, but there's also capabilities to help you verify and validate what you develop and then connect that into certification workflows as well. Now, a user story for certification with model-based design is from Leonardo, who developed a new radar navigation software using model-based design and certified this at, I believe, DAL A as well for DO 178C. Right? So again, this was radar navigation software to be used for search and rescue missions on helicopter. And they needed to certify this because it is an airborne software. And they used model-based design for tasks such as tracing requirements to the design model, generating certifiable code, automating the simulations, software in the loop, processor in the loop simulation tests as well. And then finally, generating the many reports needed for this certification effort, right? And through using model-based design, they were able to vastly reduce the resources needed to go through this certification and recertification cycle as well. And even quadrupled the rate of testing here, right? So a lot of great benefits seen here from utilizing model-based design for certification workflows. So that brings me to the end. I know I covered a lot of topics in this introductory session, but hopefully you are able to understand the overall workflow involved with utilizing MATLAB and Simulink for developing autonomous aerial systems. And MATLAB and Simulink could really help you in innovating with development of aerial systems, including developing novel types of aerial systems beyond multi-rotor and fixed wing to VTOL, incorporating autonomous technologies from perception, motion planning to controls, leveraging big data with the analysis capabilities, applying AI technologies, and then deploying your application with code generation as well, right? So again, this brings us to the end of this presentation, but hopefully this gave you a good understanding of how MATLAB and Simulink could be used for developing novel autonomous aerial systems. Thank you very much for your time.